Okay, so let's just dive right in. Have you ever stopped to think about what actually governs the behavior of, well, literally everything? The salt on your food, the phone in your hand, the air you're breathing right now. It all comes down to this incredible secret code, a fundamental language that's written inside every single atom. And today, we're going to crack that code. It really all starts with this one kind of huge question. Where does every single electron in the universe actually live? And the answer, which might surprise you, is that it's super organized. They're not just buzzing around randomly. No, each one has a specific designated home. And that home is what we call its electron configuration. I want you to think of it just like a unique postal address for every single electron. It tells you its energy level, its subshell, its orbital, is basically the atom's version of a street and house number. And this address, it dictates everything about how that atom is going to act. So, how do we figure out these addresses? Well, like any good building plan, there are rules. You can't just put things anywhere. So, let's go over the rules of the building. Okay, rule number 1, and this is the big one. Electrons are kind of lazy. They will always take the lowest energy spot they can find. It's just like filling up a stadium for a concert, right? Everybody wants the best seats, right down front, close to the stage. You fill up that front row completely before anyone even thinks about sitting way up in the nosebleeds. Well, atoms fill their energy levels in the exact same way. Let's actually see this in action. Take hydrogen. It's the simplest element. It's only got one electron. So where does it go? Yep, to the very first lowest energy spot available, the 1s orbital. So its address is just 1s1. Easy enough. Okay, now let's build on that with helium, which has 2 electrons. The first one takes that prime 1s seat, and the second one just hops right in beside it, filling that orbital completely. So its configuration is 1s squared. And that first row is now totally full. So what happens with lithium, with its 3 electrons? Well, the first 2 fill up that 1s orbital, just like in helium. But now that level's full, so the third electron has to move up to the next available spot, which is the 2s orbital. And chemists actually have a cool shorthand for this. We can use He to represent that full inner shell, and just write the configuration as He2s1. And this pattern just keeps going, nice and predictably. We fill the 2s, then we move to the 2p orbitals, adding electrons one by one until we get to neon. And with neon, that entire second energy level is completely full. So far, so good. The rules are holding up perfectly. But this is where our story takes a really interesting turn. All right, welcome to the plot twist. Just when you think you've got all the rules figured out, we run into a few fascinating rebels. These are what we call the stable exceptions. Let's take a look at chromium. Now, if we follow our stadium seating rule, we'd fill the lower energy 4s orbital first with 2 electrons before we put the last 4 into the 3d orbitals. That would give us an expected configuration of Ar, 3d4, 4s2. Makes perfect sense. It follows our rules to the letter, right? Well, nature has other ideas. Because when we actually look at a real chromium atom in nature, we find something different. Instead of what we expected, one electron from that 4s orbital has actually jumped up to the 3d orbital. Now wait a minute. Why on earth would an electron move to a higher energy level? That seems to break our most fundamental rule. And the answer, the clue to this whole mystery, comes down to one single powerful word: stability. It turns out there's this special low-energy stability that an atom gets from having a subshell that is either exactly half full or completely full. It loves that symmetry. So by promoting one electron, chromium gets a half-filled 4s subshell and a half-filled 3d subshell. That little bit of energy it costs to make the jump is more than paid back by the huge win in overall stability. And this isn't just some one-time fluke with chromium. The exact same logic plays out with copper. We'd expect it to be 3d9, 4s squared. But instead, what does it do? It promotes an electron from the 4s to the 3d orbital to get a completely full, ultra-stable 3d subshell. Its real address is 3d10, 4s1. So it all really boils down to this one idea. In the atomic world, stability is king. It is the ultimate goal, and it's what drives all chemical behavior. Atoms will bend and sometimes even seem to break the simple rules if it means they can get to a more stable, lower energy state in the end.
Okay, now for the final big reveal. It turns out these electron addresses aren't just random facts about individual atoms. They hold the secret to the master plan of all of chemistry, the periodic table itself.
So how does this work? Just look at lithium, sodium, and potassium. They're all sitting right on top of each other in the same column on the periodic table. Now look at their electron configurations. See that? They all end in S1. They all have exactly one electron in their outermost shell. And that is absolutely not a coincidence. It's the reason they all behave so similarly in chemical reactions. And this is the whole point. These addresses are not random at all. They are the fundamental blueprint for the entire periodic table. The very shape of the table, with its different blocks and rows, it's a direct visual map of how these electron orbitals are filled. The S block, the P block, the D block, it's all right there, hiding in plain sight.
So you see, the address of an atom's electrons doesn't just tell you where they are. It tells you who their family is, how they're going to behave, and ultimately why all the matter around us is structured the way it is. So if this is the code for all matter, you have to wonder, what other secrets does it hold?